Okay, now I'm going to give an example that actually arises in physics. This is a toy model of a more general model, but we'll present it using lamps, and then I'll tell you the context of physics later. So suppose you have D lamps, so D is bigger than or equal to 2, all of which are switched off at the beginning. So this is an on-off process, so you'll basically switch on or switch off lamps. So what you do, so this is how the on-off process goes. Choose a lamp at random and switch it on. Okay, so you have D lamps, choose one of them uniformly at random and switch it on. Then choose another lamp at random independently of the previous choice and also independently of the configuration of the lamps. So by configuration, I mean right now you have exactly one lamp on, but you don't know which one. So configuration can be off, on, sorry. Off. The last one is on, or first one is on, all others are off. The second one is on and all the others are off, and so on. This is one of the configurations. Although the configuration is of course random because you chose one of the lamps at random. So your next choice would be independent of this configuration. Okay? And what you do is, now the lamp that you chose can be one of the lamps that are still switched off, or it can be the one that you already switched on. If it's the one already switched on, you switch it off this time. If not, that means if it's still off, switch it on. So in other words, what you do is you change the configuration of the chosen lamp. So from on to off, or off to on. And then you repeat these steps 2 and 3 repeatedly. So let me go over it once more just to make it clear. So you have D many lamps. D is bigger than or equal to 2. First you choose a lamp at random and switch it on. Initially all of them are off. So choose one lamp at random and switch it on. Now you choose another lamp at random independently of whatever you have done before, namely which lamp you chose, and independently of the configuration of the lamps, and then change the state of this lamp. If it was on, then switch it off. If it was off, then switch it on. And then you go on repeating this procedure. Every time you choose a new lamp, every time you choose another lamp at random and uniformly among all the lamps, independently of the previous choices. So you may choose the same lamp again, as possible, and also independently of the configuration of the lamps. And then the one you choose, you change the configuration of that particular lamp. So you go on making this change. But the way we will denote it is, we are going to denote the configuration of each lamp as 0 to will denote off and 1 will denote on, as expected. Now for each n bigger than or equal to 0, for each non-negative integer n, let's xn denote the vector of configuration of the lamps after n changes. So n changes meaning, first you choose one of the lamps at random and you change the state of that lamp, right? From off to on. Initially everything was off. That's the first change. Then you choose another one at random and change the configuration of that lamp, right? So that's the second change and so on. So after n changes, the configuration vector is xn. Now this configuration is basically a vector. You have lamps, lamp 1, lamp 2 to lamp t. For each, you put 0 or 1 depending on whether the lamp is off or on. So more precisely, x0, which is the initial configuration before the changes, is 0. It's a 0 vector, all zeros. Everything goes off initially. After the first change, you will have a random variable x1 which takes values e1, e2 up to ed with equal probability. And what are these EIs? These are the standard basis vectors. In other words, EK has the kth component 1 and all the other components 0. So this basically tells you that if you choose the first lamp and switch it on, then x1 takes the value E1. If you choose the second lamp and switch it on, then x1 takes the value E2 and so on, all the way up to ET. And these are all happening with equal probability. So x1 takes these values E1 to ED with equal probability. So as we said, for each non-negative integer m, xm denotes the vector of configurations of lamps after m changes. So clearly, as I said earlier, x0 is the zero vector with probability 1, and x1 is uniformly distributed among all the standard basis vectors E1 to ED. It is not difficult to observe that xm is a Markov chain on the d-dimensional discrete hypercube S, which is essentially z2 power t or 0, 1 power t essentially. Okay. With the initial distribution, A is delta 0, this 0 is the vector 0. So this is the same notation, is the Dirac delta probability on the vector 0, which means this puts mass 1, this distribution puts mass 1 on the vector 0 and 0 everywhere else. So since you start with all lamps off, this is the initial distribution. And what is the transition matrix? So the transition matrix Pij, where each ij are basically vectors configurations, is given by whenever the difference between j and I is one of the basis vectors, then this probability is 1 over t, or it's 0 otherwise. Now this Markov chain is called the simple random walk on z2 power t. And note that z2 power t is a group. So what you are seeing is basically simple random walk on another z2 power t. Now, why is it the simple random walk? If you look at the graph of z2 power t, all you are doing in that graph is at every stage, you're starting from origin, vector 0, and then moving to one of the neighbors at random. And then wherever you are, you're moving to one of the neighbors at random and so on. So you're always in the graph of Z2D, you're just moving to one of the neighbors at random, uniformly at random. That's why it's a simple random walk on Z2 power t.